Hello friends, my name is AJ and welcome to lesson 1 of the Data Structures and Analysis series. In this video, I am going to be talking about a very important computer science concept, recursion. Now, if you watch this channel for some time or watch the AP Computer Science series on my channel, I did actually make a video already on recursion because recursion is a very important concept for introductory computer science. That would have been the Unit 10 video, and the link is in the description for that. However, this video is simply going to be going a little bit over a review on the concept of recursion. Many of you who are watching the data structures course probably took an introductory computer science class, whether that be in high school, in college, or just online, and recursion was likely covered. However, recursion is a very important concept going into data structures and analysis because some data structures are built recursively and you have to also analyze recursive algorithms. So it's very important to have a good foundation. All right, so without further ado, let's get started. All right, so we first come to the question of what actually is recursion, right? And recursion is basically the idea of a method or a function running itself inside of itself, right? So recursion here, recursion, right, is the idea of a method. And if you're using another language, it might just be called a function as well, running itself or calling itself inside of itself. Inside of itself, right? You might be wondering, well, how does this actually happen? Well, I'm going to write a very quick example. I'm going to be doing this in Java, as well as a lot of the examples in my videos will be in Java. However, you are free to kind of convert this to any language you like because the premise is quite simple. So let's say I go over here and I have a function or a method that returns an integer and takes in an integer. So in Java, you write this by saying here public int. I'm just going to call this function f. And then my input here, I'll just say is x, right? And then I have open and close parentheses. So basically, the idea behind a recursive function is that in here, you are returning, so you return f, right? And then you modify something here. So I could say, for example, x minus 1. Right? This is a fundamentally recursive method. Now, this is a very bad recursive method. I'm going to get into that in a second. But the idea is that inside of the declaration of f, or this function f, I am calling the function again, right? It's kind of this weird thing. Like you're making a function, but then inside of the function you're making, you are referring to the method that you are making. It's pretty crazy, right? Now, this is, you would think that, well, if I run x, right, if I run f, let's say I run f of 5, right? Well, this is just going to keep on going forever because f of 5 is going to return f of 4, right? And if you run f of 4 is going to return f of 3. And f of 3 is going to return f of 2, and this is going to go all the way on, right? Like I could be here, f negative 2000 is equal to f negative 2001. This just keeps going on forever. Right? And this is the problem known as infinite recursion, right? Infinite recursion, where basically you have a function that is recursive, but because it keeps calling itself and there's just no end to it, it just keeps on going forever. And that is, of course, really, really bad. So when we actually write good recursive functions, we can write recursive functions that call itself, right? But that actually end up stopping at a certain point, right? Or we hit some sort of base case, right? That we are going towards and that we're stopping at, okay? So there are very important conditions to prevent infinite recursion, right? So to prevent infinite recursion, right? To prevent infinite recursion, number one, the input that you're actually providing into the function every time does need to get smaller, or at least move towards the base case, right? So the inputs of the function need to move towards the base case, right? The base case, right? And then actually in your code, the second thing is that you need to handle the base case so that it doesn't actually return a recursive call, right? It actually returns something like just a number, or returns something as a final result, and that ends the recursion, right? So the base case needs to end, or needs to, I guess, not contain a recursive call, right? Contain a recursive call, right? Now, maybe a better way that I can now write this function, right, is I can say over here, right? So this is a very bad example because it leads to infinite recursion. But let's say I want to say here, there's a public int, and then let's say I say f again, and I'm going to say f of x in the same way I did, right? But then what I want to do is I want to provide a base case. So when my f, or when my x actually reaches 1, it's going to return the number 1, right? So if x is equal to 1, then you're going to return 1, right? And now, because my base case has now been established at 1, my inputs of x need to start moving towards that value, right? So let's say that I have a function, like let's say I have this x, and my x is 50, right? I need to start getting that closer and closer and closer down to 1, right? So a way that I can do this then is I can say else, right? And then in my recursive call, right, let's say I say return, right, f of x minus 1, right? Now what's going to happen is all my values, whenever I put in any positive integer into this x, right, is going to be moving closer to this base case, and eventually it's going to stop, right? Remember here how we have this thing going all the way down, right, to pretty much forever. Well, instead of it calling f, it's going to eventually equal 1, right? So for example here, let's say I run f of 5 again, right? So f of 5, right, this is saying that, well, is the input equal to 1? No, it's not, so it's going to return this, right? So this is going to equal f of 4. And this will be the same. See, f of 4 is equal to f of 3 because, 4 is not equal to 1, so therefore it's going to return fx minus 1. I could do this again, so f of 3 equals f of 2, and then finally I hit this f of 1, right? Where, well, sorry, actually, I have to do one more. F of 2 is equal to f of 1, but eventually I reach this f of 1 case, right? And f of 1, well, x is actually equal to 1, so now my value here is 1, right? My value is f of x is equal to 1. But now I can kind of almost do reverse substitution here, where now that f of 1 is equal to 1, well then f of 2 is equal to f of 1, this is just 1, right? So now f of 2 is equal to 1, right? F of 3 is equal to f of 2. Well, if f of 2 is 1, then f of 3 equals 1, right? F of 4 is equal to f of 3. Well, we know that f of 3 is equal to 1, so this equals 1, and so on. And this keeps happening, and then we finally get a result here that f of 5 is equal to 1. Now, of course, this particular recursive function isn't really, that useful because it's just returning 1. But now I'm going to be showing an example of where it actually shows something different. So this is a Java code block. And again, if you're using another language, you can follow along as well. The only thing that changes really is just the header of the method here, but all the other stuff should be fine. Also, I'm pretty sure here that there's some issues with the braces. Now they see that, so I probably have to add one down here, and the indent for this needs to move backward. But we'll just go with this for now, right? So let's say we have this function here, mystery, right? So we have this recursive function. Now, how is this a recursive function? Well, we can see here immediately and very clearly that we have this recursive call, right? We're returning here, let me see if I can actually just draw this in a box. We're returning here 3 times mystery and -1, right? And the name of our function is mystery. So this, by definition, is a recursive call. But we also have a base case here. We have a base case established of n equals 0. So when n is equal to 0, 1 is going to be returned. So we know that this is not necessarily going to be a recursive or an infinite recursion. Now, there is actually a case where this could be infinite recursion, and that's if we input n going to be less than 0. So if we input an n, like let's say we input -2, then it's going to keep going toward negative infinity and go farther and farther from the base case. So when you're writing these functions, it's really important to also know what your inputs are, because if your inputs are going to be negative values, you need to be very careful with kind of the direction that your call or your recursive calls are going, all right? But we're going to try and analyze this, and we're going to try and find the result here of mystery 5, right? What is mystery 5? Well, what I can do here is very simply, I can do very similar to how I did above. I can write here mystery 5, and I'm going to abbreviate. So I'm going to say here mystery equals m, just so it's easier to write, okay? So when I say m5, I'm really saying mystery 5, right? So mystery 5, well, if we look here, the first thing that it comes to in our code block is this if statement, right? And is 5 equal to 0? Well, no, it's not. So it's going to return this, right? So what is this returning? Well, this is going to equal to 3 times mystery 4, right? Because you have n minus 1 and n is 5 in this particular case, okay? So m of 5 is equal to 3 times m of 4. Well, obviously this does not really help as much because now we need to, continue going. So let's say I have here, I have m of 4 now, right? Because we need to get a value here so that we can, give a final result. So m of 4, well, we can do the same thing. Is 4 equal to 0? No, it's not. So it's going to return 3 times m of n minus 1. And n is 4, so 4 minus 1 is 3. So this is going to return 3 times m of 3. Well, what is m of 3 equal to? Well, m of 3 is going to be equal to 3 times m of n minus 1, which is 2. Why is that? Well, again, 3 is not equal to 0. So this if statement, right, is passed, and we go to this else statement, and we see that we return 3 times, mystery n minus 1. We can do the same thing again here. So we can say m of 2, and m of 2 is going to be equal to, well, 3 times m of 1. Because again, 2 is not equal to 0, so we have to go to the else statement. Again here, m of 1, well, is 1 equal to 0? No, it's not, so we go to the else statement. And this is going to be equal to 3 times m of 0, right? And now we try and solve for m of 0. Well, is 0 equal to 0? Well, yes, it actually is. So now, instead of returning the recursive call, we're going to return our base case, which is 1. So this is going to be equal to 1, right? And now we have stopped calling mystery, right? There's no more recursive calls here. So now what we can do is we can begin to do that, like this backward substitution, right? So we see here that, this here we know is our base case. M of 0 is equal to 1. Well, we can now go one layer up, and we can see that m of 1 is equal to 3 times m of 0 here, right? However, m of 0 now we know is 1, right? We know that this value is 1. So now we can say that m of 1 is equal to 3 times 1. What is 3 times 1? Well, this is equal to 3, right? And now we can go up again. We can go up another level, right? So we can say here that m of 2 is equal to 3 times m of 1. Well, we know that m of 1 is now 3. So now m of 2 is equal to 3 times 3, which is 9, right? We can go up again here now. We know that m of 2 is equal to 9, so m of 3 is equal to 3 times m of 2. Well, this is 9, right? So 3 times 9 is equal to 27, right? And again, we can do this. So m of 4 is equal to 3 times m of 3. Well, we know now that m of 3 is 27. So this is 27, and 3 times 27 is 81, right? So we say here that mystery 4 is equal to 81. And now lastly, we can get up here, which is our final case, right? So we can say here that, m of 5 is equal to 3 times m of 4. Well, m of 4 is equal to 81, right? So now what is 3 times 81? Well, 3 times 81 is 243, right? It's 243. And you can, if this is not necessarily the most trivial thing, just do 81 times 3, and this is going to be, it's going to be here 243, right? So now we can say with confidence that mystery 5 is equal to 243, and 243, that integer, will be printed out. Isn't that pretty cool? So you can see that we have this recursive function, but after kind of breaking it down and writing it out, we were able to compute the final result of this function, or of running this function, rather. And now we can look at a second case, which is a very interesting one. So if you notice here, we can try and break this down and see what makes it a recursive statement again, right? So you can see that this is a recursive statement because we are calling f. In fact, we're calling f twice, right? Our function here is f, and we're calling f twice, but we're calling a function that we made inside of itself. So this is going to be our recursive call. And then here you can see that we actually have two base cases. We have n is equal to 0, return 0, and n is equal to 1, return 1. And sometimes, depending on how your recursive method is kind of constructed, you will need multiple base cases, right? So we can actually go and write all of this out again, okay? So we're going to do that here. All right, so now what we can do is we can write this out. So I'm going to say here, I'm going to use the same color. We're calling f of 5. That's what we want to try and find the result of. So I'm going to say here f of 5 equals, well, we know that 5 is not equal to 0 and 5 is not equal to 1, so we are going to be going to this else block here, and we're going to return f of n minus 1 plus f of n minus 2. So this is going to equal to f of 4, right, because n minus 1 is 4, plus n minus 2, which is going to be 3, right? So we get this f of 5 is equal to f of 4 plus f of 3. Right? Well, what do we need to actually solve for now? We need to solve for f of 4 and we need to solve for f of 3, right? But we're going to solve for f of 4 first. Well, f of 4, if we were to kind of, go down these again, right? 4 is not equal to 0, 4 is not equal to 1, so we end up in the else statement. So this is going to equal to f of 3 plus f of 2, because again, 4 minus 1 is 3, 4 minus 2 is 2. So now we also need to account for f of 2 here. Now we can try and solve for f of 3. So again, 3 is not one of the base cases, so we have to return f of n minus 1 plus f of n minus 2, right? And so now we need to go down here to f of 1. Right? And f of 2, well, f of 2 is equal to, of course, f of 1 plus f of 0, because 2 is not one of the base cases, and 2 minus 1 is 1, 2 minus 2 is 0. Now we have f of 0 here, right? So f of 1, well, f of 1 is actually a base case, right? Right here. So the first base case we fail because n is not equal to 0, but n is equal to 1, so we return 1 over here, right? So now one of our base cases is here. And now we also need to solve for f of 0. Well, f of 0 we know here is, n is equal to 0, which is true, so we return 0. And now, writing this out, this might help you see why we have two base cases here, right? Because we have two calls, right, which are going at different speeds, right? One is subtracting by 1 and one is subtracting by 2, right? So if I just included 1 here as a base case, right, when I get to f of, okay, let's say that this didn't exist. Let's say that f of 0 didn't exist and, this didn't exist. You'll find that in this f of 2 call, then I have f of 1, which is a base case, plus f of 0, right? And if f of 0 is not a base case, then f of 0 would have equaled f of minus 1, right? Plus f of minus 2. And now this would have gone on to infinity and it would have caused infinite recursion. So it's very important to know kind of, and keep track of the different, the different base cases, especially if you have if you have two calls to the recursive function in this recursive call, it's very important to be aware of what your base cases actually are. All right, so let me just erase this. And now we can do the same backward substitution that we did. So I can say that, well, this f of 1 is 1 and f of 0 is 0. We know that because of our two base cases. So f of 2 is equal to 1 plus 0, which is 1, right? Now I can go over here and I know that f of 2 is equal to 1, right? And f of 1 is equal to 1, right? So this should give me 2 because 1 plus 1 equals 2, right? I can now go over here and I can say, well, f of 3 we know is 2. And f of 2 we know is 1, so 2 plus 1 is equal to 3. And lastly, right, we can go over here and we can say that f of 4, well, we know f of 4 is equal to 3, and f of 3, which is down here, is equal to 2. So f of 5 is equal to 3 plus 2, which is 5. So we can say with confidence now that f of 5, well, this is going to print out 5, right? The integer 5. Now, another interesting kind of thing to look at here, and this is going to be much more important when we get to actually analyzing recursion, right? Using time complexity, like figuring out how much time it takes to actually run this kind of stuff. It's important to also look at this kind of like a little bit of a, with branches or like a tree structure, right? So if we have here, right, we call f of 5, right? So what does f of 5 actually end up calling? Well, f of 5 ends up calling f of 4 and f of 3, right? So it calls here f of 4 and it calls f of 3, right? It calls these two things. And then f of 4, well, this is going to call f of 3 and f of 2, right? And f of 3 is going to call f of 2 and f of 1, right? And then f of 3 is going to call f of 2, right? It's going to call f of 1. This is going to call f of 1. This is going to call f of 0, right? And this one is going to just be the same, right? So I'll just, you know that there's something coming out of here, coming out of here. I kind of ran out of space. But you can see that this is kind of this, this tree structure where we have like, 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and so on, number of values, at least in a more, general sense. And so this, while, it's kind of random, like you might think that it's completely random of me throwing this in here, but this is actually very important when we get to analyzing recursion, right? And we have a structure like this, right? Being able to look at it and tell, well, how fast does it run, or what's the complexity of this as n, right, increases. And so this is something that, or I guess finding the time complexity in relation to n. This is all kind of stuff which I'll be covering in the next video though, so you don't have to worry about it now. But I did want to kind of introduce this structure here, or kind of this diagram of recursion, just because it'll come in handy when we talk about actually analyzing recursive algorithms later, right? And so now I guess the last part of this entire lesson is, well, why do we care about recursion, right? Recursion is something which is, decently complex, and most of the things that you actually can use recursive functions for, you can actually use just normal loops and normal iterative functions. So why do we care? Well, recursion actually does have a good amount of benefits, and one of them does have to do with sorting, right? So a lot of times when we're sorting, if we want to break up our, our list or our thing that we're trying to sort into many sub pieces to sort it, we might use recursion there, right? So in general, recursion, I guess I can write this. I can write this a little bit. Whoops. I can write this a little bit above here. So recursion allows us to break down, right, large problems. So large problems into smaller ones. Why is this? Well, remember, every time we use recursion, we are moving our input closer and closer to the base case. So every time, the problem gets smaller and smaller and closer to kind of that base case, right? So sorting it's really useful in. It's also really useful when understanding certain data structures, right? Because certain data structures, it kind of looks like a P, so I will write it here, data structures. Because some data structures are what is known as recursively defined, right? Now that sounds really confusing, and this piece also, I'll be talking about many videos from now, but I feel like just introducing it because, it might help you understand. So let's say I have this data structure. So I'm just going to, draw out this, okay? Now this is what is known as a tree. So you don't have to know this for quite a while. This is a data structure, right? Where you have, one item which leads into many other items. And what you'll notice here is that this is something that is recursively defined. What does that mean? Well, this, right? This here is a tree. This is a tree, right? However, we can break this tree into smaller trees. There's a tree right over here, right? This is a tree, right? And this is a tree. And then we can also, right, break this down. Like let's say we had more values, we'd be able to break this down into a tree, this into a tree, this into a tree, this into a tree, right? And so that is essentially what it means to be recursively defined, right? Where you can take a data structure and within it are many versions of the same thing, right? It's the same concept of like running a function inside of itself, having a data structure inside of itself. This is recursively defined. In our code, we will actually be working a little bit with recursion then when we use these data structures. That's why including recursion, even as kind of the first video, is super, super important for kind of setting the scene for the rest of the lessons, right? And so while you don't really need to know anything about trees right now or even remember any of this, because I will be going over it in much more detail in the actual lesson for this, but it's just something to kind of keep in mind when you're thinking about why am I learning this? Why is recursion even needed, or why is it even useful? Why do I need to learn about this? All right, so thank you very much for watching. That is the end of the lesson. In the next video, I am going to be teaching you a little bit of the basics of analyzing code and analyzing algorithms. If you liked the video, feel free to like and subscribe for more content. Thanks for watching, and see you all in the next one.